correct. So what we see in this model is that this is, of course, our B0, and this is our B1, B2, B3, B4, and our B1 is positive, and our B2 is negative. So this is the normal x1 term, and this is the squared x1 term. And this means that if it goes up with a bit, or the x1, that it will be positive. But if it goes up with quite a lot, because this is negative, but it's only small, if it goes up with a lot, then this eventually becomes big, and then it will go down. So what you'll see is you'll get this sort of mountain shape. So it will go like this, because it goes up, because this term is only very small, but negative. So it goes up a bit, but eventually it's going to take over because this is squared. So if you take a very large number of x, it will take sort of over, and then it will go down. And then it becomes mountain shaped. And sometimes they actually ask for this. So what is the relation between if you take the x variables, and so if the first term is positive, so the normal term is positive, and the second term of the squared is negative, then you'll get this mountain shaped. If it is the other way around, so the first term is negative, and the second term is positive, so the squared term is positive, then it will be like this. Because for very big values, it will be positive, because then you have the squared, and if this is positive, it will take over. But at first, this one has the lead, so it will be negative. So try to remember this relationship, or you can just draw it out, and you will find it. And household size has a p-value of 0.939. Let's see if we had that as well. Yeah, we had that as well. So it's not significant on its own. But its interaction term is significant, as we can see here, because that's small. And if we have significance level of 0.05, then it will be significant. It's not significant, by the way, at 0.01, but that's a rare significant level. That's really, really small. So the interaction term is significant and positive, like I said. And what does this mean? That means that if there is a larger household, so that's x2, if there's a larger household and x1 increases, so income, then household expenditure also increases more. And that's logic, because if there is a higher income increase, if there's an income increase and the household is already larger, then the expenditure on clothing increases even more. Because if it's larger already, then if you get a bit more money, probably more money will be spent on clothes, like as such. And if you have a very small family, and if income goes up a lot, maybe it won't go up because it goes up with $1 or something per person. So for example, if you're with 3, it goes up with $3. But if you are with 8, it goes up with 8 persons. So that's what this interaction term means. Then we go to dummy variables. So what is a dummy variable? Let me see if our participant has joined. No, he has not. A dummy variable is a variable that can take two values, either 1 or 0. And it takes 1 if it is true, and it takes 0 if it's false. For example, if you have a female dummy, so if it's a female, it's true, it's 1. And if it's a male, it's going to be 0, because it's not female. And it's actually in the name, so it's called a female dummy. So if it's female, it's the true dummy, and if it's not, it's a male, so it's 0. And if you have college dummy, it's exactly the same. If someone is in college, it's going to be 1, so it's true. And if someone is not or has no college degree, it's going to be 0. And that's what I explain here as well. If you say it's a male dummy, then it's true. If it's a male, so it's 1. If it's a female, but you have the male dummy, then it's going to be 0 if it's a female. And you have to remember this very well. It's actually just common logic or common sense. But yeah, I wouldn't say you have to remember it, but you have to understand it. That if I say you have a female dummy, then it's 1 if it's female, 0 if male. But if I have a male dummy, it's the other way around, because it's 1 if it's male, and it's 0 if it's female. And why are dummy variables so important? Because they allow us to estimate models with qualitative variables. So a female dummy, of course, is qualitative. You cannot really express it in, I would say, in quantitative terms, because what does that have to do with it? But if you take a dummy, you can sort of express it in quantitative terms with this 1 and this 0. And this is an important part to understand. In a simple linear regression model with dummy variable beta 1, the difference in means of this dummy variable is u1 minus mu 0, and this stands for mean, if you recall. And the model is the expected value of y given x, which is beta 0 plus beta 1x, which we have seen before. And so this expected value is the same as the mu, because what you expect is the mean, and the mean is the mu. So from u1, if you take the x to be 1, so you fill it in, then this is going to be 1, and then you get beta 0 plus beta 1. But if it is 0, the x is 0, then you get only beta 0, because this is going to be 0. So what is the difference? The difference is beta 1. So going from a male to a female, if this is a female dummy, then the difference is beta 1. Okay? All right. Yeah, I have a little trick, and I made it red because it is very, very important. And you should not get confused by it. That's why I'm going to explain it in a bit detail. So if it says female dummy, I explain it as going from a male to a female. You always go from the opposite to the dummy. Thus, with a dummy, you always look at the change. If you go from the opposite to the dummy, here male to female. I don't know if you guys understand it the way I formulated it, but for me it sounds logic. If you don't, please ask, I'll explain it again, because this is an important part to understand regarding dummies. And for male dummy, it would thus be from female to male. So the beta 1, if you have a male dummy, it means from going from being female to a male. And if, for example, you look at the regression of a few things on wage, for example, the gender and the age, and you take a male dummy, and you say this male dummy is x1. And if beta 1 is, for example, 3, then it would mean that going from being a female to going being a male means that your wage goes up with 3. Thus, this is the dummy variable you are going to be looking at. And if it would be minus 3, and you still have this male dummy, then it would be going from a female to a male, you would have a wage that's lower by minus 3. So you always go from the opposite to your dummy variable. And I think that really helps if you just remember that. So going from the opposite to your dummy variable, then you can always interpret your model. And now we are going to do an example with still the same data set. So we have the data set of clothing expenditures, household income, number of kids, and household size. And we had made those variables ourselves, which we don't need, but you can delete them if you want. You just click the entire row and click on delete, but you can also just keep them there and not fill them in. You go to, do we do that? No, we don't do that. Let's look at the example first, or what we want to know. We have to open a new document, sorry, because of course this doesn't include the female dummy. So we can delete this one, you can save it, I won't. So we have to open 21.6. So you go to Canvas again. All the documents that you need are, by the way, in Canvas, which I've also used. I think it's somewhere in week 5. Here it is. Okay, and here we see wage and we see fem. So if it's 0, it's a male. And do we have any ones? Yeah, here are ones, so here it's a female. How many data do we have? It says we have 150, but we are never sure because there might be some missing. So that's why you always look at the degrees of freedom in your table, because if you regress it now, you get a degrees of freedom of 148 because it's 150 minus 2. But maybe some data are missing. And if you look in your table, you get actually 146. That means some are missing, and you always take the number from your table. Okay, so we have this example, and we want to test with an alpha of 0.05 if the average hourly wage of men is more than 3 euros larger than the mean hourly wage of women. Here they are going to be doing complicated with the U0 minus 3 is more than U1. And that's true. You can do it like this. Or you just say, okay, I have a female dummy, which means I have to go from a male to a female. And if I say the average hourly wage of men is more than 3 euros larger than the mean hourly wage of women. That's the same as saying that going from a female or from a male to a female, which is our direction because we have a female dummy, means that you go down in wage by more than minus 3. Because from a woman to a man is $3 larger. So the other way around is less than minus 3. So minus 4 or minus 5, you would predict. So here they're going to be doing it very complicated, and they get beta 1 is less than minus 3. But we concluded that as well. You can do it like this. So it is when we want to test if the U of 0 minus 3 is more than the U of 1, which is, this is our female dummy and this is our male dummy. And since we have the model beta 0 plus beta 1x, we get U1 minus U0 is less than minus 3. If you rewrite this, then you get this. And since this is our beta 1 should be less than minus 3. But I think you can conclude that a lot easier. If you don't explain what I told you here, then please ask again, because you might not remember this part, but you need to understand this part, I think. And I'm happy to explain it again if you don't understand. So we concluded we want to test if beta 1 is less than minus 3. Okay, then first we need to make our model. Yeah, here it is. So we are going to test this, right? We already said that. So our alternative hypothesis was what we want to test. So we want to test if beta 1 is more than or less than minus 3, sorry. And remember that the null hypothesis is always exactly the opposite. So you are going to test beta 1 more than or equal, because you always include the equal sign in the null hypothesis, more than or equal than -3. So you're going to test those, and you have your test statistic. And remember, we have 3 tests up until including now. We have a t-test, we have a f-test, and we have a partial f-test. So which one are you going to use? You can discriminate between those by saying that the f-test is to test an entire model. So you're going to test if for example, if 3 variables are going to be useful. Is that what we are doing? No, we are not doing that because we are testing only 1. So we don't have an f-test. Do we have a partial f-test? So our model has, for example, 6 variables, and we want to test if the first 3 are useful. No, that's also not what we are doing, because we are testing 1 variable, and the model also has only 1 variable. So we can't do a partial f-test. What are we doing then? We are doing a t-test. And what was a t-test again? The t-test was to test if 1 variable is useful, or if 1 variable is, for example, less than something or more than something, for an upper tilt test. And that's exactly what we are doing, because we are testing if beta 1, which is belonging to the female dummy x1, is less than -3. So we take our t statistic. And what did we have for the t statistic? You have to remember this. You have the p1, so the coefficient, minus your hinge, which you fill in. You don't fill in the other numbers, you only fill in your hinge in your test statistic, which was -3. So here you can also just say +3, which I think is easier, but this is also correct. You can leave this part out. And you divide it by the standard error of your coefficient, which was here, if you remember. So we're first going to do the model ourselves. You go to Analyze, you go to Regression, and you go to Linear. We want to put wage as the dependent, of course, and fem as the independent. Click. Okay. And here our model is. So what are we going to fill in for our F statistic? You put this on the B, and you divide it by this, or well, you do this +3, and you divide it by this. And if you do that, you have to do it in Excel. We can do it together. So, like I said, I think last time, what I usually do is I just copy. I tick it a few times, and you copy the entire number, because then you can never be wrong, because they are not actually allowed to. Was this minus? I don't think it was. Yeah, it was. Because they aren't allowed to call it wrong if you do not round off. They might say you are wrong if you do round off. So what I recommend is never round off in between. At the end, you always have to round off to 3 places after your dot. And you divide it by this number. Take it a few times, Control copy, put it in, and you get this answer. So this is your t statistic. Now we have to calculate either our p-value or our critical value. For the moment being, I will do one of them. So t dot inf. What was our probability? It was, I think, 0.95. Yeah, 0.95. And we have a degrees of freedom of 148. It's always under residual and df. 148. And then this is our critical value. It is positive. Why is it positive? It should be negative because, again, like I said, you can easily make mistakes here. But if you have come to understand what you are doing, now I immediately see that this is impossible. Because why? Why? Because I got a positive value, a negative value for the statistic, but a positive value for a critical value. So what did I do wrong? I should have put a minus here. And why should I put a minus here? Because it's a lower tilde test. And remember, Excel always calculates it to the left. So I did an upper tilde test and I should have a lower tilde test. So I just put a minus in front of it because, let me draw it out. I think this is always a difficult part. So if this is our distribution, then Excel, if I put in a distribution or an alpha of 0.05, then it calculates this entire part to the right of the 0.0, to the left of the 0.05. But I wanted it to this side. And since it's always symmetrical, or it's not in my drawing, but should be, the point here, if I cut off 0.05 here, and that's at 1.65, I think, then here is 0.05 at minus 1.65. So you just take the reciprocal of it, and you put thus a minus in front of it. And that's what they did here as well. They put a minus in front of it. So our critical value was this, and our test statistic is this. And the critical value means that a value lower than this, because it's a lower tilde test, allows us to reject the null hypothesis because it's so unlikely to be true under this realization. And this, of course, is smaller than the critical value, so, such that we say it's so unlikely that we reject H0. If we reject H0, what's our conclusion? We reject this, so we tentatively accept this. Thus, we conclude that the mean hourly wage of men, or I would say there is enough evidence, because the thing is, you cannot say this is true. You think because this is false, this might be true, but it might not. So I would say there is enough evidence that to suggest that the mean hourly wage of men is more than €3 higher than the mean hourly wage for women. And also include this mean because this beta one is to calculate the mean. It's not for one person, it's the mean. And it also says that in the question for the mean hourly wage. So you don't always have to come up with everything yourself. Sometimes you can just copy it from the question if you know what to do. Okay, do you guys understand it? I hope you do. It's a bit of repetition, but then with a dummy variable. But if you understood the t-test already, then I think this should be doable. Here we have extended the example, and we have to open a new file for this. So I'm going. It should be, I think, the next one. Probably is this one. There it is already. So I'm just going to close the other one so we don't get confused. And here we have wage and femme, so female dummy, age and education level. And age is a number, but education level has 1 and 2, 3 and 4 and 5 at the end. So that are also a few numbers which are coming back in a very small range. So we are later going to see that we can make a dummy of that as well. But first, what we are going to do is we are going to put in the extended model. To the previous model, we add age and education level. So let's do that in SPSS. We go to Analyze, Regression and Linear. You put wage in the dependent variables, and you're going to click age, education level, and fem, and add them to the independence. You click OK to make the model. So here we have our model. Here's our coefficients table, the ANOVA table. Do we have more? We have a model summary and what we have entered. Those aren't very important right now. We will look at the coefficients table. Why? Because we are again going to test if fem is useful. But now if it's useful in the entire model, so taking age and education level into account, but keeping them constant. If you keep the other one constant, so it says the same age and education level, which means keeping them constant at a alpha of 0.01. So that is already very small. So what's the chance of having it significant? That's smaller. Right. That's of course smaller because our alpha is smaller. What are we going to test? We are going to test if the average wage of men is larger than the average wage of women of the same age and education level. So what should be our hinge? Larger than. It doesn't say larger than 6. It doesn't say larger than -3. So you take 0 as a hinge. Why do you take 0 as a hinge? Because that proves that if it's like larger than 0, it's non-zero, and thus it's larger. But remember, we have a female dummy, thus the beta 3, which taking the fem as the third variable, the beta 3 is going from a male to a female. Thus, if we say, or if we want to test that the average wage of men is larger than that of women, if we go from male to female, then we have to go down in wage because that's our variable, that's our dummy variable, because it's fem, female. So going from a male to a female should be negative then. So we test if beta 3 is less than 0. So in fact, we're testing if men indeed earn more than women, but because we have a female dummy, we turn it around. And the null and the null hypothesis, then of course the other way around, testing if beta 3 is more than or equal to 0. Our test statistic is this one. It's the same as last time, but with a 3. This should be, by the way, this says SB1, it should be SB3. Let me quickly put that right so you might, so you don't get confused. Should be 3. And this is, of course, a big B. Yeah, I don't usually put it in the, like you should, in the test, you have this sort of formulator so that you're able to put this under it. But yeah, you can also put it like this, but in the test, it's required that you put it more neatly like this. But I can't do that here. Or I can, but it's a lot of work. So I won't. And then you get the value of the test statistic. And since our hinge is 0, you can get it in your SPSS output. You have fem and you go to t, which is this one minus 0 divided by this, which of course is this one divided by this, which is your t. So that's that one. Or you can take your sig, which is your significance level. And you also see that that's very big. This one is bigger than 0.01, which was our alpha. So you already see that you can not reject H0. Thus, you cannot conclude that the wage of men is higher But if we look at the t-statistic, this is our t-statistic, and we can then calculate our critical value. So you put in is t.dist, t.inf, sorry. Our probability was 0.99. It's a lower tail test, so we have to put a minus in front of it. What was our degrees of freedom? We will look in the model. It's 146. So you put in 146 and you get this as your critical value. All right, okay. So you do, oh, sorry, I made a mistake before. Yeah, let me correct it. First, do the critical value like we did, and you get this. Did we get that as well? Yes, we got that as well. So this was our test statistic. And since the test statistic is less than this, so it's very surprising under the null hypothesis, we allow to reject the null hypothesis. Thus, I conclude that if I reject this one, I can accept this one. Thus, the average wage of men of the same age and education level, you have to include that because sometimes it doesn't say you have to keep those constant. So if it says keep those constant, you include it as well and is larger than that of women. I just made a mistake, I realize. I said that by the significance level, you cannot conclude it and you don't reject H0. You do. I messed up the zeros. There are 2 zeros in front of it. And this is, of course, I don't know if you can see it well. Sorry, I'll take my own SPSS. This value, so 0.004, is smaller than 0.01. I didn't see the 0. 2 zeros. Thus, you can also, by the significance level, conclude that under the null hypothesis, the finding is so surprising that you reject H0. And you conclude that the average wage of men of the same age and education, include this, is larger than that of women. And you could, this is just a standard conclusion. I would say, given the data or given the results above, we reject H0 and we tentatively accept the null hypothesis such that the average wage of men with the same age and education is higher than that of women. But this conclusion is of course correct. So gender has 2 levels, male and female, and assume that any difficult discussion is left out. Some variables can have more levels. So if you have education, you have a primary, secondary, university, master, a bachelor, etc. There can be 10 levels, depending on how you look at it. There can be 3, maybe there are even 20, I don't know. You could take its average, say education, like they have education or they don't. So that could be a dummy variable with 2 levels. But of course, this is not accurate because what does education mean? Is education primary? Is it secondary? Is it like a mix? Is it only a few university, but then you include many, disinclude many people? So that's difficult. You could also say that going from one level to another might increase, for example, wage the same each time. So going from primary to secondary school, your wage goes up with 2 euros. And going from bachelor to master, it also goes up with 2 euros, if that's your average. But of course, this is also inaccurate. Because maybe if you go from a bachelor to master, your wage goes up with 6 euros because you have much more knowledge. And maybe the step from going from primary to secondary is bigger than the step from going from secondary to a university. because primary you learn to read, but really you don't know much yet. So this is also inaccurate. So what you could do is include a dummy for each level to look at the exact change. So you include a dummy variable for education, one for primary education, one for secondary, one for university bachelor, one for master, and stuff. For example, you take a dummy 1 to be 1 if your education is primary and 0 otherwise. You take dummy 2 to be 1 if your education is secondary and 0 otherwise. You take dummy 3 if your education is university bachelor and 0 otherwise, and so on. So for each level, so primary, secondary, you take one dummy, one separate dummy. So if you have 5 levels, you have 5 dummies. But take note, because one level is always the base level and is left out. You compare all other levels relative to this base level. If you take, for example, the master as a base level, you leave it out. And why would you leave it out? Because if you do all the dummies and you take them together, you get 1, which means that together they make the whole, and they are actually, you can make sort of a linear or a strict collinearity of it. And we already discussed, if you have strict collinearity, SPSS will leave out one of those variables itself. So if you fill in all 5 of your dummies, and you have 5 dummies, then SPSS might choose to leave out 3. But to be honest, leaving out 3 is the middle one. That might be very inconvenient. So what I would recommend is leaving out 1 yourself. So either leaving out 1, so you compare all the levels to going from 1 to, for example, 2 or 3 or 4 or 5, or leaving out 5, so going from master back to bachelor, back to secondary, back to primary, probably giving a negative coefficient, of course, because going back gives from a master to university bachelor, probably gives a lower wage, obviously. But which one do you have to leave out? Usually it's given. If it is not given, I would recommend it, but it always is given. In case it's not, then you can say, I leave out the first dummy, which is primary education here, and I compare everything relative to it. But if you do that, you always have to describe which dummy you leave out, of course, because if you choose to leave out 5, then your numbers are going to be very different, because it's the other way around, which, by the way, doesn't mean that the numerical values are the same, but that's another discussion. So if it's not given, you always have to say which one you leave out. You don't have to give an explanation, you just have to say, I leave this one out. And everything is relative to that. So how do you make dummy variables in SPSS? We had the gender variable, which was already done for us. And that was, of course, easy because we didn't have to make it ourselves. Why didn't we have to make it ourselves? Because it only has two options. So if you have your coefficient, then of course it is already going from one to the other. If you have, for example, fem, if your fem coefficient is 6 and you go from a male to a female, then, for example, your wage goes up with 6. But now you have several levels and you're going to have to make them yourself. So how do you do that? If we take the first education level to be the base level, it's not included. So we have to make 4 other levels. How are you going to do that? You are going to go to SPSS. You click on transform and compute variable. Here again, you get your target variable and your numeric expression. In your target variable, you always fill in the name. So I say D2 in this case because D1 is left out. And D2 is if the education level is 2. Because remember, I already said to you, we have education level and there are values up to and including 5. So the dummy variable, if this will return 1 if my education level is 2, and it will return 0 otherwise. So I click on OK. And now the thing is, you are going to have to do this for all of them. And I know it's a bit of work, but you don't have a choice. So you do it for the third one, you can leave it in and just switch it with 3. Click up OK. Go to transform again, compute variable. Do it for the fourth one. Click on OK. And then you do it for the fifth one. And now if you go to your output, you have D2, D3, D4, D5. And what does it do? It gets 1. So D2 becomes 1 if your education level is 2. And that's exactly the dummy variable that we want. Because the dummy variable means that it gives 1 for a certain value and it gives 0 for others. The dummy variable 2, so the second education level, should of course give 1 if your education level is 2, and it does. And for the third one, it should be 1 if your education level is 3, and it does. And for the fourth and the fifth, it does so as well. 4, and for your fifth, 1, 5. Here it starts over again, so yeah. But I think you get the point. So what are we going to do now? We have to make the new model including all these variables. Okay. I think it isn't really clear, I must say. But in the next question, we have to make a model. I have to say this isn't very clear. I was doubting about this myself. In the test, it will be clear because they always say, make this model, or do this or that. But we have to make a new model because we have to test a few things in a second. So you go to regression and linear, as we always do. And you are going to put those out for a second. And you're going to make a model that only includes the dummy variables of the education. And do you have to include the education itself? No, you don't, because you have already split it up in levels. And if you add education itself, you sort of add it twice, and that messes up your model. Because here you have levels. Here, if you add education as well, not being in levels, then you get a very weird double output, which is also incorrect, by the way. It's not just redundant, it will be incorrect. So you add only those, and you get this output. So these are your coefficients, which you are definitely going to need. Let's look at a question. Are there any differences in average wages between the 5 education levels? Okay, so what do we have to test? Do we have to test one level? No, we have to test the 5 of them because we have to see if there are any differences. So it can't be an F-test. It isn't a partial F-test either, because we have the entire model being the education levels and there is nothing beside it. So it is testing the entire model. If it is testing the entire model, then it must be a f-test, right? Because a f-test measures if all or any of the variables are statistically significant. So I already always write it down like this. Why beta 1, beta 2, beta 3, beta 4, if you start at dummy 2, right? That would be a very good question. That is because you leave the first level out. So it's going to be actually a bit confusing, I would say, because it's actually beta 1, x2, beta 2, x3, beta 3, x4, and beta 4, x5, because this tests the variable of education level 5. So that is confusing, I have to admit. That's strange. But it is because the first variable you always include is just the beta 1, and the second is the beta 2. Only here, the first variable you include is the second education level. So that's x2. And that's why it might seem a bit confusing. But if you just use the rationale that you left out the first variable, then of course it's logic that the beta 1 is the beta of x2, so the second level. And that's the null hypothesis, because the null hypothesis is always testing whether all of these are 0. And if not, then at least one of them, or all of them could be as well, or two of them, is not 0. So we write down beta j is not 0 for j is 1, 2, 3, and 4. You can also write again down beta 1, at least beta 1 is not 0, and or beta 2 is not 0 up until including beta 4, but that's more work. And this is an f-test. If we go to our output, we see that our f is very big, right? It's 16, that's big. And the significance level is 0. You, of course, if it's asked for a test that's official, like official hypothesis testing, you have to write down all the steps. But I won't now, because we've done it so often already. Of course, the significance level is very small. The f is very big, so we may reject H0. And if we reject H0, we tentatively accept H1, which means that we have enough evidence to conclude that that H1 is true, so at least one of them is not 0, and that there are differences between the 5 education levels. We don't know which ones. We would have to do separate t-tests for each one to see which one has this influence, but we conclude that at least one of them has this influence. If we look at the SPS outputs and you quickly look at the significance levels, you can see that for D2 it's very big, and it's quite, well, it would be probably small enough for the other 3. So probably the other 3 are significant and cause this effect of different wages, but probably D2 doesn't. But that's not the question. The question is whether there are any differences, and for that we can simply use an f-test to conclude that yes, there are differences. We don't know yet which, we need a t-test, but that's not the question. If they would ask which level, then you would say D3, D4, and D5. Okay? Then we have another example. Is the mean hourly wage for level 2 smaller than the mean hourly wage for level 1? since we take the first one to be the first level is the base level. So you compare everything to the base level. So these variables, or these coefficients of the variables, mean going from the base level to the other level. So from the base level to D2, and from the base level to D3. So this is not the difference between those, but it's always relative to the base level. So this coefficient means going from level 1, so probably like primary education, to a master, not going from a bachelor to a master, because it's always relative to the base level. So now we know that, we can answer the question, is the mean hourly wage for level 2 smaller than the mean hourly wage for level 1? So what are we going to test? We in fact test if the mu2 is smaller than mu1, or versus the null hypothesis, which is the other way around, mu2 is bigger than or equal to mu1. Because what is mu2? Mu2 is the average of wage 2, and this is the average of level 1. If you recall that beta 1 was the difference between mu2 and mu1. So it's actually going from the base level to the first one. And what is this difference? This difference is, of course, beta 1. As I already explained, this is the coefficient, which is B1. Don't confuse it with beta 1. It's B1 to estimate beta 1, of course. And this tells us going from the base level to D2, what's the difference? So this is our B1. And if we want to test if there is a difference or smaller than, we take a hinge of 0, because it doesn't give us a number. If it said smaller than 3, you would have filled in 3. But since it says smaller than, you take just 0. And if you accept this, that means that it's smaller than 0, so maybe -1, -3, and then it's smaller. But it doesn't ask how much smaller, so that's why you take a hinge of 0. And since we want to test only one variable, this is of course a t-test. And if we want to do a t-test with a hinge of 0, it's actually the easiest test we can do, because like I said, this divided by this, so this minus 0, which is this divided by this, you get it already from SPSS by default, and it's this number. We were now testing D2, so we get this number if I did it correctly. Yeah, we did it correctly. So the test statistic is minus 0.1167, sorry. And what's the significance level? The significance level, oh, that's very, very big. So probably it won't be significant. But let's test it now with the critical value. Do we have the critical value already? So at what level we may reject it? No, we don't. You go to Excel and you click is. You take a t-test, so t.inf, because that's for a critical value. And the probability, what was our alpha? Do we still know it? It wasn't included here. No, they don't say it, but I see here it should be 0.05. Of course, in a test that's always given clearly, but the slides are sometimes a bit messy. If our alpha is 0.05, then our probability, remember this is a lower tilde t-test, so I have to include a minus. And here I have to do it everything that's to the left. So to the right, we have 0.05. So to the left, we must have 0.95. And what's our degrees of freedom? You just look that up in your model, and it's 145. So this is our test, our critical value. And what was our test statistic? Our test statistic was this. Of course, that's not smaller than our critical value of minus 1.65. So we can, from both the t value and the significance level, we conclude that we can not reject the null hypothesis. So if we go here, we cannot reject it. And this says that we cannot accept this one. So we sort of accept the null hypothesis. And we conclude that the mean hourly wage for level 2 is not smaller. That was what we were testing. Is it smaller? But we reject this. So we conclude that it's not smaller than the mean hourly wage for level 1. If there are any questions, you can ask them. And let's do one more example, I think. Yeah, we can do one more example and then we can have a small break. Yeah, here we were. Question, what is the estimated average increase in wage when you go from step 4 to step 5? Okay, let's look at their output. I said that going from the base level to the level 5 is this increase in wage. Going from the base level to the 4th is this increase. So how can we know the difference from going from 4 to 5? It's very easy, actually. You just subtract, you take this one and you subtract this from it. Why do you do that? Because the difference between the first level and the 4th is this. The difference between the 1st and the 5th is this. The difference between them is actually the difference between the 4th and the 5th level. That's how I would do it. But there's also another way to do it. You take just the average wage for step 4, which is, these are then of course 0 because you have level 4. So dummy 2, dummy 3, dummy 5 is 0. What's the wage if you are at level 4? It's of course this one plus your constant, because you always have your constant, and then you have the value is 1 for this one because you have level 4, and you take those together, and then you get this number. And you do the same for the level, you do the same for the level of 5. So you take your constant and you take this, and if you take them together, you get this number. So the average wage for step 5 is this, and the average wage for step 4 is this. If you then want to go from step 4 to 5, what's the difference? You take this one and you subtract this from it, and you get 13.46. That's the other method. The method that I explained was this one, which I personally think is easier, but you have to understand it. So it's just taking the difference from B4 and B3. Remember my story about B3 not being the same as D4, because of course this is your first, so this is your B1, B2, B3, B4, and you take the difference between B3 and B4. That's how I would do it, but you can also do it the other way, as long as you understand what you're doing. So again, if you want to go from level 4 to 5, you can just take the difference between those because you have the constant for both of them. So the only thing that changes is going from this to this. And that's why you can just take the difference. If there are questions, don't hesitate to ask. I think we can do this example after a small break. Then we have 12 slides to finish. And I think then we can take a small lunch break. And after that, if there are any personal questions or any questions about what we have discussed, you can ask them. And if there are none, then we can start on an exam. But for now, we will take a few minutes break. So let's be back at 25, if that's okay. Then I'll see you at 25.